Good morning, everyone. Thank you for joining us today on the May IMEDS community call. My name is Christine Yu, and I am from the Reagan-Udall Foundation. Before we start, please just note that this meeting is being recorded, and we are going to keep this presentation on mute for the audience for the time being in order to cut back on the background noise. And we will take everyone off mute at the end so we can have a short question and answer period. So I'm actually just going to do the meeting right now, and Alec, I will unmute you. Hi, Alec, can you hear me?
I can hear you. Can you hear me?
All right. Yes, I can. All right, great.
Okay, good.
Fantastic. So just two quick in-house reminders before the presentation. The IMEDS program released 2 requests for proposals last month, and the deadline for submitting the proposal is June 10th. Also, IMEDS is seeking nominations for open positions on our steering committee and the scientific advisory committee. So the deadline for that would be this Sunday, May 24th. So for anyone who is interested in knowing more information on these 2 announcements, feel free to visit our website, and they will be under the announcement tab. So with us today is Dr. Alec Walker from World Health Information Science Consultants. He is also a scientific advisor to the Reagan-Udall Foundation. His presentation today is entitled Outcome Definitions, Formalizing the Process for Expert Input. And this presentation is based on a paper he co-authored that has been submitted for publication. The slides being used today were sent out ahead of the call, and you should also be able to see them on your screen. We will be posting a copy of them along with the recording on our website afterward as well. So Dr. Walker, first, thank you so much for taking the time to be with us today. And with that, I'll turn the presentation over to you.
Okay, thank you very much, Christine. And thank you to everybody who's on the call. I'm going to talk about work that I did with colleagues at Pfizer, now finished up about 1.5 years ago, in which we were addressing a question that of the utility of natural language processing terms derived from a particular data source that Pfizer was using. This is the Humedica data. And the question was this: should Pfizer go to the expense and trouble of paying attention to NLP-derived terms from medical texts in a setting where there was already a lot of structured data that was available from the same electronic medical records? In order to answer that question, we needed to devise a process that for formalizing outcome definitions, and we chose to work on a particular example that was of interest to Pfizer at the time, acute liver disease in people with inflammatory bowel disease. And to focus on that and to ask the question, how much would NLP help? And what I'm going to describe is the technique that we use to create a definition, which is really just a formalization of what people in the field have been doing for a long time in creating outcome definitions, which was to do your best job thinking of something and then look at the data to see if it works, and if something else occurred to you, and then put that back in and look at the data again. So this is at the content expert extreme of the ranges of formalizing, or at least of empirical definition of outcomes in medical records. With some luck, eventually this will be published. It's a slow process, but we're hopeful that you'll be able to read it other than my slides before very long. Several of the co-authors are on the call. Xiaofeng Zhao is the second author in this, and really was in charge of thinking through the data processing and the analysis side of it. And we worked together a lot on the on figuring out how to do this. Ashwin Ananthakrishnan, who's the third author, is a gastroenterologist at Mass General Hospital who also has an interest in the use of electronic medical records data for research. So we're all living in this world now where there's this medical text data is becoming available, and there's an important question as to whether the information that you can glean from that adds in an important way to the kind of formalized data that we've used. And a lot of us have used insurance claims data for a lot of purposes, which you can think of as an extract from the structured part of the medical record. And so here we had the structured part of the medical record, which is quite straightforward to use, and we had medical text data as well. The data source that we used was a firm called Humedica, and this is now part of Optum. And Humedica provides services to clients which are large clinics, medical care systems, hospital systems for processing their electronic medical record data. It doesn't provide the electronic medical record. It sits on top of electronic medical records that are created by a wide range of vendors, and it then works with each of its clients to extract that information into a form that Humedica can process, and then it gives back the information to the clients so they can understand their practice patterns and their whatever they want to do from the medical records. So, in a sense, Humedica is a standardized central processor, at least as I understand it, of electronic medical records data to make it useful to the people who hold the records. They also keep de-identified versions of the records and for research purposes, and this is one of those applications. And as I understand it, that would be the relationship under which Pfizer was able to obtain the data. The unstructured data, that is what was drawn out of the text, is done by a search through the text. It's really just sort of parsing the grammar, the English grammar, identifying key terms which have been drawn from a variety of sources, SNOMED and MEDRA, things like that, and attempts through the grammar, the English grammar that's identified, or maybe sometimes the location in the note, to attach correct modifiers to that, so that you can distinguish between a family history or a resolved problem and an acute problem. Those of you who have been working in natural language processing know that this is a really difficult problem when the people who write the text don't think they're writing for a natural language processing system, and sometimes they may have very elaborate phrasing that it makes a modifier, and the NLP doesn't do that. Is not entirely sensitive to a preamble and then a reflection on it. It really looks at the section of a sentence to pick out terms and modifiers. So we had the question of, is this stuff useful? Is this natural language processing derived terms, are they useful for defining, in our case, acute liver disease in a population of people with inflammatory bowel disease? And this was what we set out as our strategy. So we would take all of the data that was available to us and create a rule that would mimic expert opinion about whether or not acute liver disease was present, and also what the timing of onset was. because we were living in a drug safety world, and you absolutely have to know onset dates as well as yes/no factors in order to tap things back to drugs, which are obviously a time-varying characteristic of the patients. And so what we decided that we would do would be to create this rule, then check it against the expert opinion. The experts are Dr. Anantha Krishnan, with me as an assistant, really, and then go on to look at how well this rule would have worked if we had ignored the NLP terms, and then looking at concordance of various things. My colleague at IMEDS, Susan Gruber, has pointed out that to derive a rule when you had access to NLP and then to suppress the NLP might not give you the same rule that if you had never had the NLP you would have chosen, because you might have taken some near synonyms that were available from the structured data, so that which I take as a entirely correct general critique. I'm not sure for these particular data, having gone through it, that it would have made a lot of difference, but you can judge for yourselves. Okay, so here was what we've done, and we started off, we had to define a source population that we're going to do work in. We created an a priori screen, I'll explain that in a bit, to yield candidate cases. So the source population were people in Humedica who had had at least 2 inflammatory bowel disease diagnoses. They had been in the data for at least 6 months. They had some minimal visit frequency that was discernible, and they also did not have diagnoses from the structured data of chronic liver disease, which was a context within which we thought it would be almost impossible to identify acute liver disease, superimposed liver disease. We weren't saying that doesn't happen, but just that we thought that that was too much of a demand for this sort of exploratory analysis. We then said, all right, so what are taking that population, what would be the treatment emergent codes, which would be a kind of a minimum for somebody to have acute liver disease? And so we looked at a variety of codes that would make a person at least a candidate. So to think of this negatively, somebody who had none of these things in the structured data, we didn't imagine, and this is purely on the basis of thinking about it medically, we didn't imagine that there was anything we could possibly find in the combination of structured data and NLP which would lead us to say this was definitely a case of acute liver disease. So this was sort of reduced that source population, which we ended up calling the surveillance population, to a somewhat more manageable group. Here's sort of the flow of how people went between these. We had 32,000, put on my marker here. We had 32,000 IBD patients. 3,000 of them had markers of chronic liver disease. This took us to our surveillance population, and we ended up with nearly 9,000 people, so a big subset of the surveillance population who might have acute liver disease. So that got us to our 9,000 candidate cases. So within that, here was the strategy. We sampled 50 of them, and we, at each step, we would classify those 50 people by the machine rule, and we would create a version of the data which was friendly to clinical experts, and have the expert classify as well. And we would then compare the machine rule adjudication to the expert adjudication. And with the expert, we would improve the rule in such a way that would capture the, at least capture the expert's judgment on all of those 50 patients, as well as we could. And the idea was to keep cycling through this until the machine rule and the expert were giving the similar result. As you'll see at the end, we actually didn't have resources to cycle indefinitely. And well, one of the things I think we've learned from this is that this is not a one-time operation. That data evolve, and that this is something one might be doing, periodically in any kind of ongoing work. So our first machine rule was simply that list of candidate codes that I gave you before, candidate conditions. So these are the things that brought you into the a priori stream, and that was our first machine rule. And so at this cycle, everybody who had any of these things, and remember there were almost 9,000 of them, were classified as possible people. And then we would sample them, and we created the profiles. And here's what I mean by a profile. So this is simply the data that was in the Humedica had supplied to us, laid out in a chronological sequence. We could do the chronology by day, and it could also be broken up by what section of the file it was coming from. So you see there's a diagnosis section, laboratory sections. There were also, this is things that were derived from the NLP, and what we have below are observations, which are actually, many of them are NLP derived. This is Humedica's passing through to identify relatively easily quantifiable things. So you see an observation, there's a BMI, probably there was a height and weight in the record, a diastolic blood pressure, a heart rate, a systolic blood pressure, a weight, and so forth. And what we did was to highlight different parts of this record with that corresponded to any part of the existing machine rule. And we did this in order to make the expert read of this easier. These things are really mind-numbing records to go through, because there'll be thousands and thousands of lines for an individual person, and it doesn't have the benefit of actually reading a medical record where at least you have an ongoing story created. The person who reads it has to be, in a sense, writing the story in his or her mind as they go along, and to be doing that, it's a very high cognitive activity for somebody who actually knows what's going on in general for such patients. And then we wanted to keep in front of Dr. Ananthakrishnan and me every time something that occurred in a current rule came up, so that we wouldn't make the mistake of passing over it. So this organizing and formatting the data, so it's a combination of the rule and some fairly sophisticated formatting commands in the printout. And we also had as a header for this, let's see, remember if I have it. This header at the top is the output of the current version, some basic statistics and current version of the machine rule, or the elements that go into the machine rule as it existed at that particular time. So the expert was certainly aware of where the machine rule had identified, so a ALD onset on 17th October, and these are various flags. Fatty liver flag didn't happen, greater than 3 times upper limit of normal for transaminases, that didn't happen. There had been an acute transaminase rise greater than 3 times the upper limit of normal. This sort of corresponds to specifics of elements that went into the rule that were active at that cycle. I can't tell you whether this is the last cycle or not. So at any rate, we have the 50. It's classified by the machine rule, classified by the expert. We compare them. To the extent they're dissimilar, you say, all right, well, how you sit down with Dr. Ananthakrishnan and say, all right, here's where you disagreed. What was it that you saw on the record that led you to disagree with that? And then we would shoot for the narrowest possible summary of what he saw that led to the disagreement that was, well, it wasn't the narrowest possible. It was sort of we tried to focus in on what it was medically that he saw and how that was reflected in the record. So we didn't want to overgeneralize, but we also tried not to make it so specific that it only applied to that particular case. As I saw this particular diagnosis 12 days before the onset. So we talked about it, so what was the category that he was seeing here that led him to change it, and that changed the machine rule. And we resampled from the same pool of candidate cases. We resampled without replacement, of course, and went through the same process again. And compared. And eventually we stopped. So let me talk a little bit about this more results now. So the population that we were dealing with, I give you the general criteria. This is a tiny bit more specific as to what this source population was. I mean, the biggest filter was that it was clients of Medica, so large medical centers and hospital systems around the U.S., and then this superimposed on it. These were the a priori exclusion codes, and this came from sitting down with people who had to deal with liver disease and saying, okay, what are the things that might appear here which will make interpretation really difficult of this? And these were people that we just took out a priori as people that probably wouldn't be suitable for some kind of automated surveillance algorithm. From a public health point of view, they're obviously important. In fact, these might be the people who were most susceptible to drug effects, but we just had to accept that as this job was not for finding disease in these people. The group that we ended up with, the 30,000, as you can see, this reflects the Humedica data as much as it reflects inflammatory bowel disease. There are some things that were reflected in the general epidemiology. There's more females than males. Our population here, this is not an incident population. It's a combination of a cross-sectional population of people who newly met the criteria while they were in Humedica. And you see these are dates of first appearance in the data. Again, this is really largely administrative. The number goes down in that last period because most of the IBD is something you have for a long time, and so that last smaller number was people who were newly entering the data plus people who were newly acquiring the diagnosis. We weren't trying to identify the incidence of IBD at all. Just to know who we were dealing with, these are just quick counts of codes, structured codes that appeared here. Not surprisingly at all, number one is symptoms involving the digestive system, and these are people with at least codes for inflammatory bowel disease. And you see that what you get is sort of a mixture of the being middle-aged and older and of having bowel disease. And this data wasn't used except for us to have a kind of a background and to check the general plausibility of the population. The characteristics of the criteria. We wanted to be sure that there were people, that we were having the opportunity to see people, and so these people were getting about 9 visits per year overall if you took a population rate. There's people have different dwell times in the population. You see the median visit rate per person was lower than the overall population rate, which to me suggests that people who don't see the doctor much have a shorter dwell time in the population. They're not showing up as much. But again, we weren't using this for inference, just to calculate people. About four days a year on which you had laboratory tests done, 1 hospitalization per 10 years of observation, 2 emergency department visits. So again, just generally characterizing this population. So, and this is helping us understand since we didn't know these clinics, who were we getting data from? So we had those 9,000 candidate cases. I should say by digression that even that rule for that candidate case population, we learned as we went along that there were some people who were showing up in the population that weren't contributing at all, and so Dr. Nathakrishnan would look at it and say, why did we have this person in the candidate population who only had other specified disorders of the biliary tract and nothing else? And so we would drop that person from this culled population. And so we went on going back and forth to get to our final source population. It wasn't that we knew a priori all the criteria that we would want to use to have this population that we were sorting from. Okay, well, here's where we end up after 3 iterations of this process. And I'd really like to sort of think about the structure of this rule. So we had no a priori idea as to what the rule would look like. This is what emerged from the clinician's review of actual records and honing in on something that seemed to reproduce what he did. Okay, not surprisingly, we had some inclusion criteria, which themselves were, this is only page 1 of the rules though, brought you in. All right, so if you had some very specific codes and you didn't have some exclusion things, people often came in under the laboratory value codes. And then we also had a rule for the onset date, which we took as the first date the inclusion was met, or up to a week earlier, we could look for non-specific terms, interesting for non-specific terms of the structured or the NLP terms. Interesting, the NLP terms didn't give us any inclusion criteria except when a lab value was being reported from a clinic that wasn't from somewhere else. So sometimes we'd see lab values in the NLP data that weren't resulting from the clinic, and that's presumably people who have been referred in. Okay, so that was maybe all expectable. Interestingly, the exclusion criteria turned out to have 2 kinds. One were exclusion criteria that related to the date of onset, so that if your liver enzymes went up by more than 3-fold on a particular day, that was a flag that you had acute liver disease. However, said Dr. Nathakrishnan, not if you had bile duct obstruction within 7 days, because the bile duct obstruction could cause that. So there wasn't a general exclusion of people with biliary disease, but there was a specific exclusion, a specific time-bound exclusion that emerged in his review of the records that hadn't been part of the prior thinking when we set up the problem. And you'll see a variety of things that came up, some of which maybe we would have guessed beforehand, others of which we might not have. And the point is here that it was open enough, the process was open enough to include these things, whether or not you could have thought of them in advance. And of course, these are pertaining only to the Humedica data. They might be generalizable, but we're only evolving them within this particular set of data. There were other exclusion criteria that weren't tied to the date of onset, which have this property of, some of them maybe we should have thought of in advance. Others were based on NLP and could only come at the time. So here's the rule. The rule is inclusion, onset date, based exclusion criteria, and then general exclusion criteria. We took another 50 cases and said, all right, how well does this predict Ashwin's classification then? and within the limits of 50 cases, pretty well, not perfectly. It gets most of them and excludes most of them that he wouldn't have included, and you see the calculations here. Interestingly, when we went through that test, there were a lot of observations that we made that we know that they apply fairly infrequently because they hadn't appeared in the previous 150 cases, but they did come up in this test set. And if we had to go on with the process, we would have included now these to have modified the rule so far. So that, for example, the onset date, remember we'd said that if there was a non-specific symptom within the week before the official onset date, that we would backset the onset date. Well, we found a case where that symptom had occurred repeatedly in the record. And we said, well, no. I mean, that's an exception to that rule, that if it's occurring repeatedly, then we shouldn't use it to reset the onset date. Similarly, there were some codes that brought people in on the rule as it existed up until then, some relatively nonspecific codes, and updating the rule, we would have taken those out. There had been an exclusion based on something which is characteristic of people with inflammatory bowel disease, is something called persistent transaminase elevation, and we had on looking at this, you wanted to change the rules for that. And there was also a new acute onset one where you had just an extraordinary rise in your liver enzymes. And so if we had included those were the origins of the false positives and false negatives in the test set. And for us, it was a reminder that you're not done, and that particularly, so this was just exploring these data more, but particularly if you're doing this on an ongoing way or trying to apply this to a new data set, you would surely want to go through this process of updating your rule. By the by, this being the original purpose of the study, we found that if we just use the structured data, that we did pretty well. That we certainly did miss things that had been in the NLP, and that let's see, check my next slide here. So this is the without NLP according to the we had comparing it to the clinical rule, and then this is just comparing these two machine rules, and this is bearing in mind Susan's critique, and this is classifying everybody in the 9,000, which presumably is same thing as everybody in the 30,000. And we see that there were a number of cases where the NLP missed things, and some were added things, and we looked at those a tiny bit more carefully. Let's see. That there were things that these are things that tended to appear in the medical texts, which actually changed our decision. And the conclusion that we came from this was that for this particular example, in this particular population, using Humedica data, that the NLP was moderately helpful, and that it was maybe what one would have expected. And I think that the situation, this is speculation, is evolving from what it would have been when the clinicians in the group, if you trained more than a decade or two ago, your sense of a medical record would have been that there'd be a tremendous amount of information in the free text, because you expected other people who were reviewing the record to read your notes. Now I think people have gotten very accustomed to the idea that there are drop-down lists or that there are extracts that happen, and that people take the structured part of the data more seriously and will use the text sometimes to support the structured data. But I'm thinking, and that it is getting more and more infrequent, that people use the medical text to introduce new vital information. Because we all know that when you're counting noses, you're going to some kind of structured file. So my thought or my speculation here is that for surveillance purposes, that the NLP may be becoming less in the future, less and less important. Although for confirmatory purposes, as this becomes the medical record review, then you may still want it for those purposes, but it becomes marginal for the surveillance kinds of activities that we were thinking about. So in sum, what's our experience in this thing? First, that going from clinical definitions to the data that it's available in these real-life medical records, so non-research databases, is definitely not an exercise in code mapping. There's a lot more that we have to do, and that we think about the complexity of that algorithm for this fairly straightforward acute onset disease that involved lots of places, and it wasn't a lookup table that was going to do us that. That there's that when we're looking at creating a diagnosis, that there's a lot of considerations. The terms that we have here, both in the structured and in the unstructured data, vary tremendously in their specificity. They may overlap some one another. They may or may not relate to various aspects of timing. They often will mean something in the context of what the doctor is thinking at the time. So that and what the doctor is thinking at the time is this thing called a differential diagnosis. So that's the list of all the possible diagnoses that are compatible with the thing that you have in front of you. So you've got an elevated ALT. Well, all those exclusion criteria were parts of Dr. Ananthakrishna's differential diagnosis as reflected in specific examples that he was looking at. We didn't ask him in general, what's the differential diagnosis of an elevated ALT? We only asked him in the context of the specific cases that we were seeing. The development of the algorithm doing it in this way is clearly iterative. I think a really important piece of this that we've only begun to get at was embodied in those color codings of the clinical profiles. That is, how do we get our candidate algorithm to display nicely to a clinician in the context of the medical record that he's looking at, that he or she can be helpful in updating the algorithm. Because ultimately we had 9,000 people to classify. There was no way you were going to have Dr. Ananthakrishnan read the 9,000. We got where we got on the basis of his reading 150 of these records, and probably could have gone on before it really stabilized for another 150. But what we needed to do, having decided that we were going to incorporate his knowledge as it applied to these data, we needed to make it easy on him to do this. So I think that what we've ended up with is something that, as I said at the beginning, I think is not that different from what we've been doing a lot. Those of us who are in the applied area anyway. But what we're trying to do here is to formalize it somewhat, and to put it in a context where you end up with some sort of measures of sensitivity and specificity, and where we can talk about what's inside the algorithm and sort of keep it out of the black box. Or we were taking it out of the black box and kind of holding it up so that others can talk about what the algorithm does and whether that might generalize to their setting. So, Christine, that's all I have to say. We could maybe unmute and be happy to take questions.
Great. Thank you very much, Dr. Walker, for taking your time with us today. I will be unmuting now.
The conference has been unmuted.
So if you are not speaking, please remember to mute yourself at this point. And if anyone would like to ask Alec anything now, please just take a moment to introduce yourself and feel free to do so.
Yeah, and let me see, I have on the chat line a question already from Robert Lebuama. Hello, Robert. And how did we, for the first iteration, pick out NLP terms? And what we did was we sat down with a bunch of clinicians and we said, okay, this is the disease that we're trying to identify. What are the various words you might have written down in a medical record which are either of the disease itself or related to some kind of presentation of the disease? So we had a pretty wide range of terms that, for this purpose, we limited the NLP abstraction or listings to terms that were in that range, and I forget, there may have been 100 terms ranging from abdominal pain to jaundice to dark urine to any number of things. And we tried not to be restrictive because we knew that no matter how long the list was, it was a tiny fraction of the scores of thousands of terms that the Chematica NLP was pulling out of the medical record, and we were hoping to create something that would be a little bit, that wouldn't crush the medical reviewer with terms.
Okay, thank you.
Other questions?
Hi, Dr. Walker. This is Hugh Kawabata from Bristol Myers Squibb.
Hello.
I was wondering if you would comment a little bit about this process as sort of the, the new standard way of doing validations with EMR data rather than medical charts.
Well, we're kind of far away from it being a standard. Let me just say what is useful about this. So what we've said was that this is an iterative process for eliciting from the expert the basis for his or her adjudication of the raw data. So we can write it as a rule that could be applied to a larger set of raw data. And what we can say is this rule says the same thing that the expert does. So if the raw data you think is good enough to get an FDA level adjudication, then you're home free. You've done it. Then it becomes something you could argue would be a standard. I mean, it's clear that we're going to have an opportunity to look at these extracts in a way that we couldn't look at medical records. I think you would still want to do, before you left behind expert review of the full text record, you'd want to compare this rule against that, which we didn't have access to in the Medicaid data and we didn't attempt to do. But there's a lot of internal plausibility here. That is, if you look at the rule, and that's the nice thing about deriving it in this way, you can think about it medically. Is this making sense? And that might even lead you to say, well, kind of go beyond this. Are there other things we should have looked for? So it's not a standard yet, but I think that it could be the basis for creating standards.
Hi, this is Rich Boyce at the University of Pittsburgh. I think the work that you did was very nice and thorough. It's a great contribution to this field, so thank you for presenting this today. I didn't have any specific questions, but I thought that your point about engaging the clinicians who can really help to design these machine algorithms is really important, was a really good one. And I wanted to point out that I'll share a link on the list that there is currently a couple of projects that are actually dedicated to exactly that task that are going on in the informatics community. The leader of this work is specifically Wendy Chapman, who's now at the University of Utah, but she was at UCSD for a period of time. So I'll pop a couple of links in there. They've developed out of their laboratory some tools that you might find interesting that try to make the whole process much more usable, make it much easier to do the validation kind of work that you guys were doing, and so forth. So I'll just send that up for your information.
That's terrific. Yeah, I think that the one place where what we came out with really differed radically from what I'd had in mind coming into this maybe, and what I've seen elsewhere, is the problem is not a 2x2 table. I mean, you may reduce it to a 2x2 table, but that onset date is a real hooker here, and a lot of information is time-dependent in its interpretation. And that's where what the clinician was really useful for, is saying, this thing 6 months ago is irrelevant, this thing a month ago might be it, and this thing a week ago is the answer to why you have it. And I don't know how we would have come around with it otherwise.
Great. Any other questions or comments?
I have a very good question. This is Simone from the FDA. Thank you, Alec, for presenting this very interesting work. My question is related to what someone else asked about a while ago in terms of gold standard. I'm trying to sort of understand. So this database, I'm trying to understand how the patient profile compares to the charts for medical chart validations in terms of getting a PPV. Do I make sense? Are medical charts available in this data set that could be looked at?
No, they're not.
Okay.
Humedica does have the entire record internally, but it's protected by some pretty strict both contractual issues on confidentiality as well as HIPAA issues. So you can't, as it's currently structured, you can't really read the medical record. They have snippets, which are little bitty extracts of the text that are often less than a sentence long, from which the NLP program derived its classification, and they have extended snippets that they're willing to read, and you can work out some ways of reading with them, but that they won't deliver. But that's just peculiar to Humedica. If you were working, in a clinic, let's say you were at Group Health or something, and you actually have the data in front of you, they would have, I would presume, the actual medical record to compare it against. And their algorithms might have very different operating characteristics to this, but you would have the ability to go back to the medical record. There are some things which you would say, what I've got here I know is good enough. I'm certainly not going to say that somebody has acute liver disease if I don't have liver enzymes. So, there might be specific cases in which you can say what's here is good enough, and we can stop there.
Okay, thank you.
Any other questions or comments?
Hi, this is Susan Gruber from Reagan-Udall. Hi, Alec, thank you for a fine talk. What I like best, I kind of want to echo what Rich said, is a way of incorporating domain knowledge into then machine learning or computer techniques, I think is really important, and so I really appreciate this work. The question I have, though, when we look at the numbers, you have in the 50 cases where the experts have weighed in, the 50 sample, they identified 12 cases and 38 non-cases. So that's a rate of about 24%. But on one of your final slides where you do all 9,000, both of the machine learning, what?
No, go on.
Both of the machine learning algorithms identify more like 40 or 45% of cases in the population of 9,000. So what I'm wondering is, with a sample size of 50, how accurate do we really think those PPVs and sensitivity and specificity numbers are?
I think that they're a general indication. I mean, that 79% of that predicted value is probably somewhere between 50 and 98%. So I wouldn't want to say very much about that. And remembering that we would want to increase the rule anyway. And let's just go to so this is maybe what's worth saying here. So this is the classification among the 9,000. The 9,000 were people who had some kind of liver code that emerged during the observation, and so it's really out of the 30,000. So you could add another 21,000 to the non-case side because they possessed nothing that the machine rule could possibly have, or even that clinician probably would have created. So that that was out of the 9,000 possible cases. I see. So and what you had observed was that here, applying it to the whole population of the 9,000, that we had 4,000 out of 9,000, whereas coming out of the sample from that same population, go back to
Slide 33.
Slide 33. I'm just learning how to do this. I think this is it. That we had machine rule had only 14 out of 50, as opposed to it would have been more like 20 out of 50 applied to that whole population. So there's clearly huge amounts of sampling error here, and I would say that there's we ran out of time and money, but you would have you would certainly iterated it a couple more times, and you probably would have done your final validation in a much larger sample than 50. Oh, let me just say, one virtue of enriching that population of candidate cases, if you really can throw out people from there that couldn't possibly be cases, and is to make this proportion, keep making it richer so that you're looking at a good size, population. If we've been doing this in the full 30,000, you'd only have been expecting 1 in 10 to show up as a case, and then you've just gone on forever classifying. So there must be more efficient ways of doing this, and you can even imagine some sort of adaptive scheme where you keep enriching it. But this is where we are now.
Right. In the machine learning literature, it's called boosting. You take the samples that are easy to classify, and you stop focusing on them, and you start focusing on the ones that are difficult.
Yes.
So a boosted algorithm.
Yeah, so this is sort of boosted. I'm glad to have that term. This is the fact that we're only looking at 9,000 here is that's already culled. We've put easy to classify 21,000 aside as not having disease. And we could certainly have, there surely would have been some that we could have done on the other side as well.
Okay, thanks very much.
Great, thank you. So we have a couple more minutes left. If there's any other questions or comments now, we can probably take one last one.
And Christine, I see that Richard has already posted all these the links, so that they'll be very interesting to follow up by people who are doing similar work.
Sure, definitely.
Yeah, I'm trying to find the link to the lab. She moved her lab recently, but their lab's got more current information. Though I did see the second link is looking at temporal information extraction from clinical text. It looks like they're actually having a challenge this year at the computational linguistics conference, and those challenges tend to really help advance the field quite a bit. So that's interesting. I'll see what more information I can find. Thanks.
Thank you so much.
Right, thank you. So I guess if there's no other questions, then thank you everyone for taking your time out of your schedules today to join us. So the next community call will be on June 19th at 11 a.m. You'll see an invitation from us with the topic of that discussion very soon. Thank you all again. Thank you, Dr. Walker, and you all have a great day.
Thank you. Bye-bye.
Thanks.